Hello and welcome to our 22nd lecture, Limits and Continuity. So limits are the core idea behind derivatives, so this lecture kind of focuses on understanding what a limit means and how to calculate it in basic cases, so that the next lecture we can have a solid ground to work on from. Before we begin, I'd like to mention that while my lectures are about basics on each topic, which I'm presenting, if you systematically break down a problem, even if it's a harder one, you can successfully solve a lot of them even with just what we are doing in my lectures and mini-tests, and some logical deduction. For instance, my friend, a college student at master's course of chemistry, had a math exam, which is a high level of education, so it's obviously hard, even if she's not studying maths. And she had some problems with probabilities, so she had my video and found it quite useful, helping her grasp some basics and then solve harder examples. One of which I might solve for the next week's short video, as I do have exams of my own, so it's hard to find time for every week post, as it's been for the last month and a half, but after those exams I might try to catch up back with weekly upload every second week lectures, and in between weeks some shorter math stuff like we had with the Minecraft million and a billion video. Anyway, let's get started with why. Why do we need to know limits? Well, a limit tells us what value a function approaches as x gets close to a certain number. Even if the function is undefined at that point, the limit can still exist. This idea is what makes derivatives possible. There is a mathematical way of describing them, but perhaps that would be too much info dumping, especially if we don't work with the logical symbols and stuff. So here we can see from the image that we're looking at the behavior of the function as it is approaching the value x equals 3. Maybe it's hard to see due to low quality, but I underlined it with red. Also, we can also see it from the graph, not just the formula, because, well, the graph has these colored markings. The green area is centered on 3, selecting a certain area within the confines. Of course, in reality, we're looking for the green area that is as narrow as possible, which means it must be wide. Its width must be near 0, aka the green range is sort of a deviation from x itself, meaning the closer we get to the real x, the more precise our limit solution will be. Same with derivatives, but that's for the next lecture. After that green interval is determined, we mark the intersection of edges of green and the function, and then draw horizontal lines to get the y values of them. If all goes well, that region is also very, very small or narrow, allowing us to get a single point as the answer, or in other words, the limit of the function at a certain x value is the result. But it is important to know that the first 2 points listed here, as a limit can be different than the value. So we use limits to detect behavior near a point, and it's not necessarily the value at the point itself. So that's the main point of today's video. So future next here, as per advice of a university professor who was helping me with building my lectures and everything, he said that it is important to clarify that when you have a limit of x approaching infinity, that is based for asymptotic behavior. So if we remember asymptotes, they are values that the function infinitely approaches but never quite reaches. So 1 over x, we have the function that is always decreasing towards a 0 but will never reach it, because no matter what value you insert as x, you can never get y equals 0, which kind of can make sense because infinity itself is not a number, it's a concept. So whenever you have a concept like that, you're looking for another concept. So just keep that in mind. Limits towards infinity are looking for asymptotes, not the exact value. So what the function tends towards but will not reach, as opposed to the exact value. So a is 3, that's where you approach, so where the function tends to, but due to it being an actual number, another concept, it should reach that value. So it should reach that x, so it should have a value defined at that x. While infinity, impossible to exactly define, so exactly what number it is. In that way, it does not mean an exact value, but an asymptote. Hopefully this clears it out, and best of luck with the continuation of the lecture. But before we complicate it further, let's get the formula down. This is the general formula for a limit. Well, technically there's something missing, the equals y, but I couldn't add it because the arrow and part would be pushed to the side. Basically, you write lim, which stands for limit, then within the brackets, well, I didn't add the brackets here, but you put the function of which the limit you're solving. And then underneath lim or limit, you write x or whatever variable you have, and then arrow pointing towards a. That a is replaced by a number to which the x is approaching. So in the previous graph, like right here, limit x approaches 3. So that's kind of like that. And then what's missing here is the equals sign and then the y value. So in this example, it would be 2, like here written. Hopefully it's visible enough so you can kind of get the idea down. But yeah, under the lim part, you put the arrow. We will see, or actually I will mention other types of arrows, but usually it's from left to right. And altogether, it means that the limit of a given function of x when x approaches a is y, like is written here. I marked y, a, and x variables as bold and italics, hopefully to be easier to differentiate from letters in text. So essentially we're asking, what value does the function of x get closer and closer to when x gets closer and closer to a? As we will see later in the video, there are functions that have a different y value at a certain x than the limit is at it. So it is important to remember this. So there is basically two different approaches to determining limits. One is on a graph, and the other, more commonly used, is in numerical, especially because some graphs or functions are hard to graph. So for limits like this, we check if the curve approaches the same point. So let's say this black point here. So basically a limit is where the graph is heading at a certain value. We can check that by looking where left and right side approach at a certain x. We can call them the left and right limit. As the name suggests, they're going from the left or from the right. They are one-sided limits, important name, and when they agree, so when they give the same result, we get the limit that I mentioned before. The one-sided limits are marked like so. The left limit has x pointing to a with a negative exponent, and the right limit has x pointing towards a with positive exponent. There are lots of other markings like arrows. Instead of pointing towards a, it points up for left and down from right for right, which means basically if it's approaching from underneath, so from the left or under, lower axis to higher, or from above, so from higher axis to the lower axis. Kind of like that. I can't do those arrows in PowerPoint because when I'm using the presentation mode, it gives me like empty squares and weird symbols. So, but you can look up, I think on Wikipedia, they have a list of all those arrows, very well summed up. So I recommend checking it out if you are interested in learning limits more on your own. So how does this all apply here? Well, we check both limits for our a, which equals 4. So let's start with the blue, or right limit. We see that it is approaching at x equals a, it approaches y equals 4. So I color this limit blue, and then I equal it to 4. Meanwhile, our red limit, or left limit, approaches the x equals 4 and gives us y equals 4 as well. So, since both one-sided limits gave us the exact same answer, we conclude that the limit of the given function of x, where x approaches 4, is 4, like written here. We don't have to do both of these, we can just look how the function behaves and just write it out generally. But yeah, when you do the math more, usually you don't do these unless you have separate functions that cut off at some point. For instance, if I had a different function for red part and a different function for the blue part, then it would be recommended to use this formula. Next, we have a different example, like I just mentioned. Oh, I forgot what I genuinely forgot I had this one in. Here we have two functions, and with their limits, we're going to determine if they touch, which is another thing we're gonna do later on, but let's not foreshadow too much. Our left or red limit for a is 4 equals to 2. So we see that it approaches the y value 2 as x approaches 4. To be fair, it should have been changing the a raised to superscripted plus or minus to the number. Like here, I shouldn't use x to a minus, but it's much clearer to see whether we're using the left or the right limit. Plus, I'm kind of clarifying that a is 4, so technically here I should have x approaches a minus, but I would use the up arrow because it's approaching from lower axis to the higher. Since I can't do that, I just used this even though I should be inserting the a value. As I said before, why am I repeating myself so much? Math makes a man crazy. But yeah, hopefully in the future lectures, if I do have a chance, I can use the correct arrows. Maybe I'll try to find a different symbol as well. Anyway, now for the blue. It goes from higher axis to axis 4, so it decreases. Huh. I am dumb. Okay. So yeah, these are incorrect. Ignore it. So go back here. This one should be plus. Okay. Just keep that in mind. It seems like I forgot. Okay, all fixed. This one is plus as it should have been. Anyway, we see that it's approaching from higher part and it approaches 4. So the two one-sided limits are not equal, therefore these two functions do not approach the same y value at the x equals a, which means that this graph does not have a defined limit at a is 4. This is a very clear example of how the functions are not continuous. But what is continuity? Let's see what it is. So it is a property of a function. But when would a function be continuous? Well, it has to satisfy all three of the following conditions. The first is that the point f of a, so inserting a instead of x, must be defined. So the function must have a y value that you would get if you put a as x. As we will see later on some examples, there will be a function which is undefined in only one point. Maybe you remember from previous lectures. Today we will actually see it and solve examples with them. The second is that the limit for x approaching a must exist. So for that we need both one-sided limits to have the same values. And for final condition is that the limit as x approaches a must be equal to the value that the function has at a being the input. So there is some overlap of on the rules, but if a function satisfies all three conditions, it should be continuous. Unless I'm forgetting something, which I highly doubt because this was from Wikipedia, which is a very reliable source. Anyway, now that we got our detour into continuity from solving limits, let's continue with the types of discontinuities. We have three types. First is a whole or removable discontinuity, where only one point is undefined, but the rest of the function behaves as if there was nothing missing. We will run into at least one example today, definitely more than one example, and it's quite hard to show it on Desmos, or to be correct, to take a screenshot of it. So sadly I don't have a picture here, but I have this nice sketch I found for other types of discontinuities, so I can explain them on the examples. Yes. The second one is a jump. So when you have a mix of two functions, one is in the mini-test, on the same graph, where they have a condition so that they are only drawn for certain x values, so for certain intervals or a certain point, and this discontinuity happens or occurs where there's a certain gap along the y-axis between them. As you can see here, the left function ends higher than the right one starts, or begins, or whatever. There could be an example to solve where I give you two functions, first ends at a certain x and another continues at it, and then you have to prove that the outcome is continuous. You would have to do that by using left and right limit for the appropriate functions and equaling them, but I think that would be too easy for you guys, so I did something slightly different for the mini-test. And last that I cover is the infinite discontinuity, which is basically when the x value isn't defined as the graph goes to either or both infinities, like 1 over x for instance. Now let's move on to mathing the limit of the function. Not the right terminology, but it just sounded like a funny idea in my head. Also, this is oscillating discontinuity. I don't know what to say about this one. We'll get to this eventually down the road. So there are, again, a few steps we can take when solving limit problems. First, we have to try direct substitution. So as intuition would want you to try, is to insert the a value as the x in the function and checking if the function is defined at that point. And if it is, that is the limit. But what if that isn't the solution and we get some other results? Well, we decide what to do next based on what results we get. If we have x approaching infinity or minus infinity, we just insert a big number. I found that 1000 is usually good enough. If not, just increase the number of zeros to like 10,000, a million. Oh, there's an example using this. But yeah, usually just increase a big number and hope for the best. Or two different big numbers like 1000 and a million and then just see percentage-wise changes, because now you know how to work with percentages and relative changes. First possible outcome, as said before, is getting a number, which means we found our limit. Second is to get either of the infinities, which means that the function has a vertical asymptote at that value. Usually that's written as 1 over r, where r approaches 0. Can't say x because vertical asymptotes can be at other values other than x equals 0 as well, or when x approaches infinity for stuff like linear, quadratic, etc. And last and the most hated, but most interesting, due to the amount of the steps they demand, are the indeterminate forms. They're all the interactions we can have when infinities, like 0 divided by 0, infinity divided by infinity, 0 to the, times infinity, infinity minus infinity, infinity plus infinity, 0 to the power of 0, infinity to the power of 0, 1 to the power of infinity, and so on, a lot more. So let's see an example of each. Because what's point in blabbering about theory when we can just solve examples? So we have a function 3x plus 1, and we have a limit when x approaches 2. So let's do direct substitution by putting x as 2. We copy the formula, or the function, insert x as 2, and we get 7 as our limit. Which, if we check the graph, like the one I included here, we see that the graph does approach y equals 7 at x equals 2. Well, the output of the function, if we put 2 as x, would be 7. So yes, this works. Second way is if our limit is infinity, meaning the more we approach the right x, the more y goes towards an infinity, preventing the graph from touching that x value. Well, I'm sure we know of a person with such a power. But let's get back to math and our example for vertical asymptotes. So we will insert 0 as x and we get undefined. Technically this isn't infinity, but infinity is undefined by itself, so it technically gives us the same result since the graph does not approach both infinities, like we see here on the next slide. But yeah, so the result was undefined, since we cannot pin it to either infinity, as left limit is negative infinity and the right one is positive infinity. But yeah, this is the second possible outcome of direct substitution, the result being undefined. And for our last outcome, our example would give us one of the indeterminate forms. Aha, big words. So let's insert 1 as x. We copy the function, we insert 1, and we get 0 divided by 0, which, if we remember from our rational functions, I think. But let's check the graph. We see that the point x equals 1 is undefined. This means that our graph isn't continuous, but we clearly see that technically there is a value that the function approaches, and the value of the limit is definitely not 0 divided by 0, meaning there must be something we can do to solve it. Well, there is. Now, to solve the indeterminate forms, we have 3 ways, again the number 3, of solving limits that give such results after direct substitution. First way is to factor out the part that causes the 0 or infinity. So for example, in our 0 divided by 0 solution, if we cancel out the common factor that would cause the 0 divided by 0, we could maybe see the real result. We can do that as the factor itself is not 0 in majority of the cases, which builds up the behavior of the function, which makes sense as you're looking for the formula of the function that behaves on the same, exactly the same in all the points except this one specifically. But more on that in the example shown after I list all 3, because why would I give example after each if I can just list them all and just go one by one? Anyway, the second one would be conjugates. If we still remember from complex numbers, conjugates were when you change the sign in front of the imaginary term. Essentially, you can do the same thing for radicals or roots by making sure you can get rid of them, per formula of difference of squares. And third and last would be using trigonometric identities, or just identities in short, which I will just show because they will be handy next time. Very handy next time. So let's bring back our example we used before. We know substitution would give us 0 divided by 0, so let's try factoring numerator to find the common factors with the denominator. We see that we have x minus 1 factor on both sides, because if you still remember the formula for the difference of squares, we break it apart, we get this, we cancel out the common factor, and we're left with x plus 1. So as we see, if we inserted x equals 1, these two terms or factors would equal to 0 divided by 0. So when we cancel them out, we see that the original function does indeed behave as x plus 1 function. So our limit we can change and rewrite this as this. So the limit of this function equals to the limit of this function, which equals 2. And as we can clearly see, it does approach 2. And if you want to graph this function by itself, you'll get something like this. This is again just a repetition of rational functions. I think that's their name. I genuinely just forgot, like I blanked. But yeah, just a repetition of them and the property like this, because that's where most of these cases are going to be happening. Anyway, for the example of conjugates, we have a limit of this wonderful function, which I'd hate to have to draw manually, so thank God, or well, Eli Luberov, for making Desmos. Anyway, let's try to substitute and solve the limit for the lazy way first. So we copy the function, insert 0, we get 1 minus 1 divided by 0, and we get 0 divided by 0 again. So let's use conjugates to get rid of the radicals. If only it was that easy to solve the problems of dangerous radical people in real life. So here is our function, and we multiply both sides with the conjugate of the numerator. Yeah. I know I told you to simplify fractions by getting rid of radicals from the numerator, but here we would rather have them there for some reason, I think. Probably to rationalize the fraction to make it easier to work it with. So we just multiply back. So as per difference of squares, a plus b times a minus b equals to a squared minus b squared. So we can see here, this part squared minus this part squared is this. So the root just disappeared. And the denominator is just x times the entire conjugate part. So 1 minus 1 is 0. And we're left with x and this thing. We cancel out x's, because we see that if we inserted x as 0, we would have 0 divided by 0. So that all cancels out, and we're left with 1 over this thing, which doesn't look much prettier, but who are we to judge something by its appearance? And which we can see by desmosing it, or by just inserting 0, we can get our limit at y equals 1/2. So yeah, I could just put a 0 here, and then like 1 divided by 1 plus 1 is 1/2, or putting it to Desmos. That is our limit of this function at x approaches 0. Fun, right? Now for our trig identities, we have the first trig identity, and probably the most important one of them all. Sine of x divided by x. So direct substitution would give us 0 divided by 0, but by now we know that this isn't the end. Of course, or I wouldn't use it as an example, of course, especially as an identity. In this example, this is the identity, as I mentioned before, which will be quite more useful in the future, probably, pretty sure, in physics at least. I definitely don't see the future, so don't worry about it. Anyway, I'll show you a graph of the behavior of them to make it clear, as me just saying the answer might not be clear enough. So I have both of the functions graphed, and we see that for small values, they're nearly identical. So like, I don't know, what's this, like 0.25, 0.33. So within the interval of minus 0.33 to 0.33 as x, these two are pretty much the same. So for smaller x's, x approaching 0, the limit would be 1. Now, we can also see the entire function here. As the x increases to infinity, or negative infinity, it approaches to 0. However, when x is small enough, or near 0, it's gonna be equal to 1, which is, of course, the solution in this example. There is another way of showing this. Now, imagine a giant pendulum swinging left and right. Now, imagine it stops in its resting position, and imagine that the rope is like super long. Now let's imagine I displace the weight at the end of the rope just ever so slightly. If the angle of displacement is small enough, it would look like we moved the weight completely straight horizontally. Because sine of x, which is the distance that we displaced it on the horizontal line, as we hopefully still remember, would seem equivalent like x, for small x's of course. Another example would be Earth. It's huge. Well, not as huge as some other stuff, like planets and stars of course, but still relatively big compared to us, the observers. Here let's say that the length of the line is x, like this. The left top part of each rectangle represents the distance from the surface. So x of each respective rectangle is proportional to the distance listed. So let's just say as the distance increases, so these numbers increase, so would x. We see that if we look at the small enough distance, relative to Earth's radius, surface would look nearly flat. As we approach 11 kilometers, we start seeing a curvature. And fun fact, 11 kilometers is roughly 0.2% of Earth's radius, and we can already see the curvature. And as that increases to 0.4 or 0.6, etc., or even 2%, we can already see the curve. So that is when the x value is, the x value is so great that the sign of x no longer gives us 1. If we go higher, you see more. And then the more you see, the more it curves. Kind of like that. So they diverge. So for small x's, this is 1. For greater x's, this is no longer 1. This will be useful in physics when we're working with pendulums again, so we can just replace or simplify certain triangles and stuff like that. This is more a fun fact than actual math. I'm not doing the formulas because that's physics. But yeah, it becomes even more visible at 22, etc., or even 100 kilometers and so forth. Basically, this is the first identity we can use. The second one is the limit was x towards infinity. It would approach 0. But yeah, we use these identities to solve examples like the next. So here is our example on how we actually solve it using the trig identities, or just identities in general. We know that the first identity is that x approaching 0 limit of sine of x divided by x equals 1. But here we have sine of 3x divided by x. So let's write down everything we know. I changed x to v for the identity so it's easier to differentiate. We also see that we need to divide sine of something with that exact something in it. So we have 3x in the sine function, we would need 3x in the denominator as well. Now how would we get it? By multiplying both sides of the fraction with 3. Like this. Since the 3 would cancel out, this wouldn't make much of a change just solving it, but it helps us simplify stuff. I haven't covered the rules for calculating limits because it's easier to do so when you understand what limits are, so we will do them in a bit. But here I can show the first one, and that is the product rule, or coefficient multiplication rule, which states that the limit of the product is the product of the limits. How would this apply here? Like this. We broke the limit apart along the red line, so along the operation, so the product, and we rewrote it as the product of two limits, where each limit has their own function, like in itself. Now we can simplify these individual limits from what we have learned so far. So limit of 3 when x approaches 0 is 3 because, well, we can either just know it because 3 is not dependable on x, or just inserting x as 0 wouldn't change it. And then the limit of sine 3x divided by 3x is 1, since we could replace 3x with v to get the generalized rule. And basically the input to the sine function and then the denominator are the same, which is the main condition for the rule, well, along with the x approaching 0, but this is a given in this example. So the second limit is 1, giving us a result of 3 times 1, which is 3. Well, and here is the graph to show we did it right. Of course, the point at x equals 0 is undefined, but the limit is still there at the point 0,3. I just couldn't get the selection, but if you graph it in Desmos, you can clearly see when you hover the point up here. Now, so limits follow predictable rules. Now that we have made an introduction into them, it's easier to present them. Why do these rules exist? To make it easier to solve certain examples, like the previous one, predicting other limits or generalizing behavior, whatever that means. First is the sum and difference rule. It states that that the limit of a sum is a sum of the limits. Same idea goes for the subtraction, of course. So if you have a limit of a function plus another function, you can break these two apart as long as this part is the same, or combine them if that might so help you. For an example, x squared plus 3x, we can break this h of x function into f of x and g of x, and then separate them like this, which for this specific example would be 4 plus 3 times 2, which is 10. On to the next rule. It is the product and constant multiple rule. The latter one we have seen before, so basically any time there is a multiplication, just like we did before, like you could also do x squared like that. Separate, in this example, you can break it like x squared times, limit of x times limit of x plus limit of 3 plus, times limit of x. So you can break down to the basic parts. But yeah, Just like we did before with addition and subtraction, you can separate the factors into separate limits, or in the example with a constant, we just carry it out as the limit of the constant is basically a constant itself. Like in this example, a limit of 5x squared where x approaches 1. It's 5 times limit of x squared where x approaches 1. I could break this one apart again by doing it 5 times limit of x when x approaches 1 times limit of x when x approaches 1. But that just gives the same result, so 5 times 1 is 5. Simple, right? And lastly, the quotient rule. This one works the same as all before. The limit of a quotient is a quotient of the limits. I would add an example to this, but it wouldn't show anything new, as it would basically look the same way as we solved it before with substitution. So just putting it, putting in a instead of x, and we would get a fraction to solve for, etc. So nothing new, we've all seen this. Now, where do these laws not apply? Well, first is if a limit does not exist. It is pointless using those rules, as any change in outcome will most likely be incorrect. And second is when you get division by 0. Then you just have to use simplification methods we mentioned before. Now, for the end of this video, I will introduce a very interesting limit, the limit of 1 plus 1 over n raised to the power of n, where n approaches infinity. So just like with the sign identity, here we have the same value in the denominator and the exponent, with the 1s on numerator and the addition. Which is important if you ever run into an example with this, as you might have to transform the exponent through radicalization, so roots, or changing the fraction. So let's try to solve this with substitution. First, I'll replace n with x to make it easier on the mental gymnastics for those who have harder time switching variables. And now I copy the function and insert infinity. Because we know 1 over infinity is practically 0, right? And then 1 plus 0 is 1, and 1 to infinity is surely 1, right? Well, no. If we remember back, 1 to the power of infinity is indeterminate result, meaning that we need another way of solving this. Also, 1 over infinity is near 0, but not exactly 0, and when we have a number, even if it's infinitesimally, however, small, greater than 1, raised to some exponent, eventually that number will increase. But to where? Well, let's try to do it with just a big number, let's say 1000, and we'll do substitution again. So I insert 1000 instead of the x. We get 1.001 to the power of 1000. We see that we get the result 2.71692, etc. We get a certain number, but is that the result? Is it close to it? Well, let's insert a million just to see the comparison. So I insert the million, we get this number to the power of this number, and we get 2.718280, which is a very small increase from the previous number despite doubling the zeros, or 1000 times bigger number. Well, it turns out that if we keep increasing the x towards greater numbers, the y or the limit will approach the value e, because this is approximately e. So this limit will approach the Euler's number, or constant, or whatever you want to call it, as x increases. A very handy formula for a lot of examples that contain stuff like this. Also, important to note, using the rules before, if we had a situation like this, where the inner part is raised to some extra exponent that I marked with ax, you can break it apart by using one more bracket set over the entire thing, where you have a over the entire thing inside, like this. Sadly, it's hard to see as the sizes are super different, but I hope you get the idea. The exponent to an exponent is basically exponents multiplied. So that would be e to the power of a. But yeah, so if the exponent is different like this, then the result isn't just e, it's e to the power of a, which kind of makes sense using the rules, as the exponent would be done over the result of the inner limit, so multiplying e's together would give us e to some power. And fun fact, this is an extension of the original limit, which is what's more often used in problems. So yeah, one more thing, it's crucial, the couple of rules that you have to remember for this identity is that you have to have, have 1 here and 1 in the numerator. So if there ever isn't a 1 on the left or here, you may have to make sure to format the fraction so that it is. which will make whatever is in the denominator the x. So if you had a 3 here or a 3 here, you have to reformat this inside of the bracket in a way that you will get 1 plus 1 over something. Whatever that something underneath here is, that will be x. Yes, this is a hint for the mini-test, so do remember this. Speak of the devil. That's all for the limits, as they're useful for understanding derivatives next time. And here is the mini-test, to which I wish you best of luck. If you have any questions, ask them down below. I'm glad to help. Feel free to join my Discord link down below to ask any questions that you might have. Thank you all, and I'll see you all on our next quest. Bye!